Hello, everyone, and this is Chapter 5, Mathematical Reasoning of CCCS122 Discrete Mathematics. So, in this chapter, we'll learn about mathematical reasoning, and we need mathematical reasoning to check if mathematical arguments are true or false, and to construct more complex arguments. Mathematical reasoning is also used to, like I said, conduct proofs and program verification. And it is essential in AI systems, which draw inferences from knowledge and facts. We focus on deductive proofs here. Before we move on, some basic terminology. An axiom is a basic assumption about mathematical structures that needs no proof. So it is basically another word for it is something that is common sense, can be called an axiom, something that needs no proof. A proof demonstrates that a certain statement is true, and a proof consists of a sequence of statements, and we'll see a lot of that in the first half of this chapter. We'll see a sequence of statements, and that together form an argument. And those statements are usually based on rules of inference, which we already covered in good detail in chapter 1. Fallacies are cases of incorrect reasoning. A theorem is a statement that has been shown to be true. A lemma is basically just a smaller theorem, something that is proven as part of a larger theorem usually. A corollary is a proposition that follows directly from a theorem that has been proven. And conjecture is just a statement whose truth value is unknown, meaning it's kind of like a statement that doesn't have a proof. Once you prove it, that statement becomes a theorem. A theorem often has two parts: conditions, meaning premises or hypotheses, and a conclusion. Now, a correct proof is one that establishes that if a certain condition is true, then a certain conclusion is true. So conditions to conclusions is a tautology. Now, often there are missing pieces between condition and conclusion, and those are filled in by arguments using conditions and axioms, and using the rules of inference. We basically fill in those pieces, and that is what we call a mathematical proof. Now, like I said, we'll be going back to using rules of inference extensively in this chapter. So, rules of inference provide the justification of steps used in a proof. An important rule is called modus ponens, or the law of detachment. Comes from Latin, and its literal translation is something like method of putting by placing. And it is based on this tautology. So what this says is if P is true and if P is Q, then Q must also be true. Now, we will usually be writing these in this form, basically putting them one on top of the other. So what this basically means is the first line over here means P alone means if P is true, and connecting the first and the second line is basically an and. And if P, then Q. So if P is true, and if P, then Q is true, therefore, and that's the conclusion, that means that Q is also true. Now, the general form of a rule of inference is like this. We have uh, statements piled on top of each other, and one connecting to the next, leading us to a conclusion. Each rule in here must be a tautology. And another way to write this is basically this. So basically, statement up here connected by an and together they mean that the conclusion is true. Now, we can use the rules of inference without proving them every time in order to generate a larger proof. And here are some of the rules of inference that we will be using in some of the examples coming up. So there's addition. So if P is true, therefore P or Q must also be true. Here's another one. If P and Q is true, therefore P must be true. So it's called simplification. If P is true and Q is true, therefore P and Q must also be true. So it's called conjunction. This is familiar to us. If Q is not true, and if we also know that if P is true, then Q is true, and therefore that means that P is not true. This one is called modus tollens. This is also Latin, and this translates something like method of removing by taking away. And then we have another one. If P, then Q, and if Q, then R. Therefore, that means that if P, then R. And this one's called hypothetical syllogism. Last one for now. If P or Q is true, and if we know that P is not true, then that means Q must be true. This one's called disjunctive syllogism. Just like a rule of inference, an argument consists of one or more hypotheses and a conclusion. This word that you just saw, syllogism, also comes, it's English, but it comes from the Latin word syllogismos, which means conclusion or inference. We say that an argument is valid if, whenever all its hypotheses are true, its conclusion is also true. But if any hypothesis is false, even a valid argument can lead to an incorrect conclusion, and we'll see an example of that. So, for proof, show that if a hypothesis is true, then a conclusion is true using rules of inference. So over here we have an example. It says if 101 is divisible by 3, then a 101 squared is divisible by 9. 101 is divisible by 3. Consequently, or therefore, 101 squared is divisible by 9. Now, it sounds pretty logical. If 101 is divisible by 3, or I should say, if 3 divides 101, then 9 divides 101 squared. And then we go on to say 101 is divisible by 3, which means 101 squared is divisible by 9. Is there a problem here? Now, the argument is valid, but it is incorrect because the initial hypothesis 101 is divisible by 3 is incorrect. And because the initial hypothesis 101 is divisible by 3 is incorrect, that means the conclusion is also not true, is false. Now, in this above statement, if you replace the number 101 with the number 102, 102, you can quickly check. 3 does divide 102. Then this whole statement that you saw up here, all of it becomes true. 102 is divisible by 3, which means 102 squared is divisible by 3 squared, or 9. Okay. So, question. Which rule of inference was used in this last argument? So we have two propositional statements, P, let's call the first one P. 101 is divisible by 3, and the second one, Q, 101 squared is divisible by 9. What we basically said was P is true, and because if P is Q, then Q is true, therefore Q is true. This is the one that we called modus ponens. However, since one of the hypotheses, the first one, is false, therefore the conclusion is not guaranteed to be correct either. Here's another example of an argument. If it rains today, then we will not have a barbecue today. That makes sense. Don't want to have a barbecue in the rain. If we do not have a barbecue today, then we will have a barbecue tomorrow. Therefore, if it rains today, then we will have a barbecue tomorrow. This is a valid argument, and if its hypotheses are true, then its conclusion is also true. So let's rewrite that using formal notation. So first proposition, call it P, is it is raining today. Second proposition, Q, is we will not have a barbecue today. And the third proposition, R, is we will have a barbecue tomorrow. So this argument is basically of the form that if P then Q, if it is raining today, then we will not have a barbecue today. Followed by, if we will not have a barbecue today, then we will have a barbecue tomorrow. That's the second line that you see, which leads us to conclude that if it is raining today, we will have a barbecue tomorrow. So if P, then R. This is the one we called hypothetical syllogism. And yet another argument. So we have a couple of statements here. Gary is either intelligent or a good actor. If Gary is intelligent, then he can count from 1 to 10, not a very high bar. Gary can only count from 1 to 2. Therefore, Gary is a good actor. Let's see. Let's rewrite that in more formal terms. So, proposition I, propositional statement I, Gary is intelligent. So giving it the label I for the use of the word intelligent in here. So we'll see that frequently being done in examples to help you remember which proposition is representing which statement. So I stands for proposition I is Gary is intelligent. Then we have proposition A. Gary is a good actor. That's proposition A. Then we have propositional statement C, which is Gary can count from 1 to 10. Okay, so first thing that we know is Gary can only count from 1 to 2, so he cannot count from 1 to 10. So that means not C. That's our hypothesis. And we also know that if I, then C. And because of not C, that means I can also not be true. And that is modus tollens, step combining steps 1 and steps 2. That leads us to conclude not I. We also know that either Gary is a good actor or Gary is intelligent. So A or I. Because I is clearly not true. Therefore, A must be true. This is called disjunctive syllogism, combining steps, information in steps 3 and 4. The conclusion is, therefore, that Gary is a good actor because he can't count. And one of the two had to be true. That's a short version of it. And another example. So, if you listen to me, you will pass CCCS122. This is an if-then statement. It's a conditional statement. So, you passed CCCS122, which means Q is true. Therefore, you have listened to me, or you did listen to me. So that must mean that P is also true. Question is this argument valid? And the answer is no. It assumes that if P, then Q, and if Q is true, then P is true. Now, this statement is not a tautology, and is false. If P is false and Q is true. Also, some rules of inference for quantified statements. These are pretty straightforward. So the first one is this one. So if for all x, P of x is, of course, a predicate, a propositional function. So for all x, P of x, therefore that means P of C is true as long as C is from the universal set that's being talked about over here. So if this general statement, if the statement about everybody is true, then this statement, this predicate function, propositional function, this predicate, must also be true for some individual member in the universal set. This is called universal instantiation. Now, if you can also go the other way. So if P of C is true for any C from the universal set U, that means we can rewrite that like so, and therefore that means for all x, p of x. This is called universal generalization. And then we have another one. For some x, p of x. This means that, therefore, p of c is true for at least one element c out of all possible elements that could be passed to predicate as an argument. This is called existential instantiation. That's kind of going again the other direction, starting with p of c is true for some element c out of U, the universal set. That means, therefore, for some x, p of x is true. This is called existential generalization. And here's an example that uses these quantified statements, these rules of inference for quantified statements. We have as an example, every UJ student is a genius. Abu Bakr is a UJ student. Therefore, Abu Bakr is a genius. In predicate form, that would look like this. So we have predicate U, predicate function U of x, which stands for x is a UJ student. And then we have another predicate g of x, which stands for x is a genius. Now, you can use these steps in the argument. Step one is, what was the statement again? Every UJ student is a genius, right? So for all x, meaning all possible students, if the student is a UJ student is a genius. That's the hypothesis. Step two is universal instantiation. So if this hypothesis is true for all students, all UJ students, that means that if Abu Bakr is a UJ student, then Abu Bakr must also be a genius. And since Abu Bakr is a UJ student, therefore Abu Bakr is also a genius. This is an application of universal instantiation. Okay, let's talk a little more about proofs. So one way to prove things is the direct proof, the direct method. So have an implication. If P, then Q can be proved by showing that if P is true, then Q is also true. And here's an example. For a direct proof of the theorem, if n is odd, then n square is odd. And the idea is that if we assume that the hypothesis of this implication is true, so meaning n is odd, and based on that, we show that the implication n square is odd is also true. And throughout this, we will only use the rules of inference and any known theorem to show that Q is true if P is true. So, we began with n is odd, then that means n can be rewritten as 2k plus 1. Why are we doing that? 2k, this part, is of course an even number. So k can be in here as any integer. 2k, by multiplying any integer by 2, you're making it an even number. And then by adding 1, the number is guaranteed, the whole thing, the sum is guaranteed to be an odd number. So n, we begin by rewriting it as 2k plus 1. So if that is n, then what does that make n square? N square becomes just the square of 2k plus 1. We open up that square term and we get 4k squared plus 4k plus 1. We can take 2 out as a common factor out of the first two terms, and we can rewrite that like so. Now, we don't care what's in here. All we care about is that it's some integer, and of course it's in here you're taking the square of an integer, which is an integer, multiplying it by another integer, 2 in this case, and you're adding to it 2 times another integer. And we don't care if it's even or odd. All we care is that this part over here is an integer. And then that integer is being multiplied by this 2, meaning that this part over here is an even integer. And then we're adding plus 1 to it at the end, which means that this whole thing is an odd integer. And that's what we wanted to prove, correct? Since n squared can be written in this form, it is odd. We also have something called the indirect proof. And in this one, an implication, if P then Q is equivalent, we know that it is equivalent to its contrapositive, meaning if not Q, then not P. Already seen that a few slides ago. So what we do here is that, therefore, we can prove if P then Q, we can prove that by proving that whenever Q is false, P is also false. That is an indirect proof. So let's begin with an example again. So let's find an indirect proof of the theorem if 3n plus 2 is odd, then n is odd. So let's assume that the conclusion of this implication is false, meaning the conclusion is n is odd. Let's flip that. N is not odd, meaning n is even. Now, if n is even, then let's prove that, then use rules of inference and known theorems to show that P must also be false. And what was P? 3n plus 2 is odd. So meaning, show that 3n plus 2 is even. So the opposite of n is odd is n is even, and the opposite of P is 3n plus 2 is the opposite of odd, even. So we'll go from here to here. Indirect proofs are a special case of something called proof by contradiction. So let's suppose n is even. Remember, that's the negation of the conclusion. So we'll write n as 2k, where k is again some integer. 2k is guaranteed to be an even integer. So we had the other term in 3n plus 2. Let's substitute 2k in place of n. We get 6k plus 2. We can take out 2 as a common factor. And we get 2 times 3k plus 1. Again, k is any integer multiplied by another integer still makes an integer. And we add to it 1, making yet another integer. So this whole thing that I underlined over here is all an integer. When you multiply it by 2, it is guaranteed to be an even integer. And if you go back quickly, 3n plus 2 is even. This is what we had to prove. And therefore, 3n plus 2 is even. And therefore, we've proven what we set out to prove. However, this is a contradiction since 3n plus 2 is given to be odd. That's the actual statement in the proof that we were trying to prove. So the conclusion, n is odd, holds. Okay. Another example. There's a lot of them in this chapter. So anyone who performs well is either intelligent or a good actor. Someone is intelligent, and he can count from 1 to 10. Gary performs well, and Gary can only count from 1 to 3. So therefore, not everyone is both intelligent and a good actor. So predicate P of x is x performs well. Predicate I of x is x is intelligent. Predicate A of x is x is a good actor. And predicate C of x is x can count from 1 to 10. Now the statement anyone performs well is either intelligent or a good actor can be rewritten in predicate form like so. Anyone meaning everyone. Who performs well, if they perform well, is either intelligent or a good actor. That's a direct translation of this statement up here. If someone is intelligent, then you can count from 1 to 10. So for everyone, they're intelligent, then you can count from 1 to 10. Try a direct translation of that statement. We know that Gary is among those people who performs well. So P of G is true. And we also know that Gary can only count from 1 to 3, meaning that he's not among the people who can count from 1 to 10. So not C of G. And that lets us conclude that not everyone is both intelligent and a good actor. Because we found Gary, right? So, not everyone is both intelligent and a good actor. And here's the same thing done using another method, or done differently, I should say. So, we began with the initial hypothesis that for everyone, if they perform well, then they're either intelligent or a good actor. That's step 1. Now, this was a general statement. what we use universal instantiation on step one, and we take this statement in step one, which is a general statement true for everybody, and try to fit it on our guy, Gary. And we know that Gary performs well, which means that this whole thing that we had up there is true for Gary. He's either intelligent or a good actor. If he performs well, then he's either intelligent or a good actor. And then we're also told that he does perform well. So P of G is true, which means that the conclusion in step 4 must also be true. He must be intelligent or a good actor. And we also know that for anyone to count as intelligent, they need to be able to count from 1 to 10. So, if Gary is intelligent, he must be able to count from 1 to 10. But we know that he is not able to count from 1 to 10, which means he is not intelligent. So, either he's not intelligent or he is not a good actor. Apply the De Morgan's law to this, you get this or sign flips to an and you get not intelligent and a good actor. Then apply existential generalization to the previous step, step 9, to step 10, I'm sorry. And we get that there are some, meaning there exists x, for some x, it's not true, it's not the case that x is intelligent and a good actor both. And then you can take this operator outside of the quantifier, which flips the quantifier, of course. And we have, it's not the case that for all x, they're intelligent and good actors. So, put even more simply, not everyone is both intelligent and a good actor. So in this section, in this half of chapter 5, we learned some basic terminology necessary for mathematical proofs, the rules of inference, valid arguments, hypotheses and conclusions, construction of valid arguments using rules of inference, and the difference between direct and indirect proofs. And there are other types of proofs, but these are kind of like the two most important ones.